All right, let's go ahead and review some things we talked about in our last couple of lessons. We had some theorems that I refer to as our location theorems. And so we've got to make sure we're careful. There's really two concepts. We just got to keep them straight. We said that every point that's in the bisector of an angle must blank. What's true about every point in the bisector of an angle? Victoria? Yeah, it's equidistant from the sides of the angle. What about every single point that's equidistant from the ends of a line? Every single point that is equidistant from the ends of a line. What's true about those points? All of them must lie where, Victoria? Yeah, in the perpendicular bisector of that line. So therefore, if a point is in the perpendicular bisector of a line, then what must be true about that point? Gotta be equidistant from the ends of the line. And of course, if a point is in the bisector of an angle, then that point is going to be equidistant, class, from the, and there's no class in here, sides of the angle. Good, Victoria. We talked about lines that will, oh, by the way, one more quick thought. We said that if you have just 2 points that are both equidistant from the ends of a line, 2 points that are equidistant from the ends of the line, those 2 points will determine the perpendicular bisector. That's actually the basis of construction 1, is finding 2 points, one above, one below, equidistant from the ends of a line. We'll talk more about that when we get into some constructions and show alternate ways still using that fact to do construction 1. We talked about lines that meet in a point, 3 or more lines that meet in a common point, and we said those lines are referred to as concurrent lines. Victoria, in case you haven't figured it out, this is one of my re-recordings. There's no class in here, so you're answering everything. And you're doing great so far, by the way. I heard you. I'm just kidding, I lied. But concurrent lines, good job. We talked about 3 sets of concurrent lines in our last lesson. And the first set of concurrent lines met at a point called the circumcenter. The question is, which lines intersect at the circumcenter? The perpendicular bisectors. Here's how to remember it. It's the circumcenter. It is the center of a circumscribed circle. So if it's the center of a circumscribed circle, then the distance here, here, and here must be the same. Therefore, this point is equidistant from the ends of the lines or the sides of the triangle. So circumcenter, picture the circumscribed circle, okay? The circle that goes around. Circum means around, scribe, to draw. Picture the circle drawn around. Picture the center of the circle and realize it's got to be equidistant from the 3 vertices. Therefore, if it's equidistant from the ends of lines, it must lie in the perpendicular bisectors of those lines. Okay, or of those sides. So the circumcenter is where the perpendicular bisectors meet. But we also said that the angle bisectors of a triangle have to meet. And remember what we call the point where all the angle bisectors meet. Remember, if it's where the angle bisectors intersect, then it's equidistant from the sides. Equidistant from the sides of the angle or the sides of the triangle. So you could put a little circle, poorly drawn in that case, but you could put a circle inside. It's the in center. So perpendicular bisectors intersect at the circumcenter. Angle bisectors intersect at the in center. We had another set of lines that also intersect, and these are the altitudes. They come straight down or go straight across or straight across. They're all going to meet at a point as well. And we said technically, if you made parallels to all 3 sides, you get a larger triangle. And if you were to circumscribe a circle about that, this would be the center of that circle. It's kind of stupid, frankly. So we said we really don't get into that as far as the circle and all that nonsense. But I did say there's an easy way to remember these altitudes that go straight down or straight across. And we said that the lines that go straight across these altitudes meet at a point called the orthocenter. Did you know that, Victoria? The orthocenter. And again, ortho means straight. Think about the orthodontist, makes your teeth straight. So the orthocenter. So 3 centers. Circumcenter, perpendicular bisectors. In center, angle bisectors, orthocenter altitudes. Or maybe you need to know them the other way, or really both ways. Maybe you need to know that the altitudes intersect at the orthocenter, that the perpendicular bisectors intersect at the circumcenter, and that the angle bisectors intersect at the incenter. Okay, make sure you know those. By the way, coming back here, we said that this circle here, because it passes through all the vertices of the triangle, it's drawn around. We described the circle as being, what was that word again? Yeah, circumscribed. But we said that the polygon then is said to be inscribed, where here it's the polygon that's drawn around the outside, circumscribed, and the circle's inscribed. But you need to know that if all the vertices lie on the circle, it's an inscribed polygon, and if the circle passes through the vertices, it's a circumscribed circle. All right, let's go and take a look at the homework that you had in the last lesson. And you were given a triangle, ABC, as usual. You were given the midpoint of, excuse me, you were not given the midpoint, you were given a median. Hopefully you mentioned something about a midpoint, though. If you didn't, fix your proof, pause the video and fix your proof real quick. So we were given triangle ABC. We were given a median. Ding, 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 ding. Page clang. What does median mean? It's a line that goes from a vertex to a midpoint. So hopefully we're thinking midpoint here. Call this point M. And then we extended AM. And we also drew the parallel at C that would be parallel to AB. So through a point, only one straight line, we draw parallel to a given line. We drew that parallel, and eventually, because these two lines are not parallel, since this line is parallel to this one, this line and this line will not be parallel, so they must intersect, and we call this point of intersection P. We can go ahead and erase the excess and simply mark the point of intersection. So, given triangle ABC with median AM, we were told that AM was extended to meet a line from C at P such that CP would be parallel to AB. Okay, probably the easiest way to word that. And we were asked to prove that triangle ABM is congruent to triangle PCM. All right, so let's go and get down your two columns, your statements, your reasons. For sake of time, I'm not going to copy down my first statement again, having written it once. I'll simply draw a little arrow up here. And of course, our first reason, I'm lazy, but one word, I'm not that lazy. All right, number two, I've already alluded to it. Clang, median. Median means we have a midpoint. And if we have a midpoint, we need to say we have a midpoint. We should state that M is the midpoint of BC. Reason? Hopefully you said definition of median of triangle. You see, do I have to specify median of a triangle? Yes, because median means different things depending on the shape, right? So want to specify we mean triangle. We need to say M's the midpoint. Now, if that wasn't statement number two, that's okay. You could have had it a different number statement, but it should have been one of the early statements. If you didn't have that, you're going to have a hard time. Because knowing that M is the midpoint, clang, 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 that clangs us another direction. What does that mean if M is the midpoint? Yeah, well, you ask yourself, what's a midpoint? It's a point dividing a line into two equal segments. So that means that BM and CM are equal to each other. And reason there, definition of midpoint. Now again, you had to have these in this order. Now, there could have been something else before 2, but you can't have 3 before 2. You can't say BM and CM are equal before you specify you have a midpoint. There is one other clang here, though, that you should have identified, and that's your parallel. I've got parallel lines. Clang! What's the outcome of parallels? For our purposes, we would say equal angles. What kind of angles are equal when you have parallel lines? Alternate interior angles, alternate exterior angles, sometimes some corresponding angles. Well, notice here, if I call this angle 1, and I could call this angle P, but just for sake of ease, I'm going to number it angle 2. These are alternate interior angles, aren't they? For that matter, if I call this angle 3 and this angle 4, and of course you could have numbered them whatever, I've got some alternate interior angles here as well. Now, you could have made this your second statement, because all you needed was the fact that there were parallel lines to say that my angle 1 equals angle 2, and angle 3 equals angle 4. Again, your numbering may have been different. Make sure that you have the correct angles, though, regardless of how you numbered them. And we'll say that's because we said what kind of angles again? Yeah, alternate interior angles. So we should say alternate interior angles are equal? Are alternate interior angles equal? If lines are parallel, right? So we should specify alternate interior angles of parallel lines are equal. And so I've got, looking at what I'm trying to prove here now, I've got my plane taken care of, right? I'm trying to prove that ABM, that's this guy, with this angle and that side, are equal to triangle PCM, which is this guy, with this angle, and that side. Well, it looks like we've already got congruent triangles by, yeah, side angle. Just write that in there. My side angle, here's my sides. There's my angles. There's my other angles. Now, you could have taken a sixth step. You could have said that these two angles, let's call them 6 and 7. I don't know what happened to 5. A 6 and 7, maybe this is 5. But they're equal to each other because vertical angles are equal. Then you could have done angle, side, angle instead. But you would have had to specify the vertical angles were equal. Nothing wrong with that. Takes one more step. Not a problem. One more step doesn't hurt anybody. That's really the only good ways I can think of to do the proof. If you had something else, you're like, hey, I didn't do it that way, but I think I might have gotten it, or I think I was close. Certainly, Victoria, send me a picture of your proof, and I'll take a look at it and see how you did, and give you some feedback that way, or do a Zoom call or Facebook video chat where I can look at your proof and talk through it with you. All right, hopefully, though, you did well with that proof. Really, it was all Clang until the very end, and the Clang had already taken care of everything you needed. So I thought a pretty straightforward proof. Theorems, corollaries, section of your notebook. Theorems, corollaries, section of your notebook now. And we talked about 3 sets of concurrent lines in our last lesson. We're going to talk about one more set of concurrent lines today with Theorem 31. Theorem 31 in your textbooks, or in your notebooks. We've said that the 3 perpendicular bisectors of the sides of a triangle meet at a point. We've said that the 3 angle bisectors in a triangle meet at a point. We've said that the 3 altitudes of a triangle meet at a point. Here we go, Theorem 31. The 3 medians of a triangle meet in a point. The 3 medians of a triangle meet in a point. And in parentheses, if you would, put the word centroid. C-E-N-T-R-O-I-D, centroid. Okay, the centroid is what we call the place where the 3 medians of a triangle meet. So remember the median, just by way of review, even though we just had one of these in our homework proof. Remember, go to the midpoint. So vertex to midpoint. We find the midpoint, vertex to midpoint. We find our midpoint, vertex to midpoint, and this point then would be called the centroid. Okay, if it's where the medians meet. Flip back, if you would, to terms definitions real quick. Let's put it in second place like we did with the others, and let's write this down in terms definitions as well. Centroid, and simply say the intersection of the medians of a triangle. The centroid is the intersection of the medians of a triangle. Again, the centroid is the intersection of the medians of a triangle. Once you got that down, if you would turn to page 311, or excuse me, 111, turn to page 111, and let's take a look at Theorem 31 as listed in your textbook. Now, what you'll notice is what I had you write in your notebook is not what's in the textbook. The textbook has some extra information about this centroid that, frankly, I don't care about, but it is kind of interesting, so I want to point it out to you, and I also want to point out the proof, which gets very challenging, frankly. Very difficult proof to work because of the extra that's in Theorem 31, but it's kind of interesting. Page 111 in your textbooks, Theorem 31, you'll notice it says the medians of a triangle meet in a point, that's the centroid, which is 2/3 the distance from each vertex to the midpoint of the opposite side. That's where the difficulty comes in finishing the proof because of the way the book has it. But basically it's saying if you were to take this entire distance, the length of the median, and you were to measure off 2/3 and then the last 1/3, you would get those 3 segments. Same thing here. You measure off 1, 2, 3. 1, 2, 3. So it's 2/3 the distance. Now, I'm not going to require you to memorize that. Frankly, it makes the proof more challenging, which the proof is done in the book already, okay, admittedly, so I'm going to allow it to stand for itself there. We're not going to put it in our notebooks. You're going to see why as soon as you turn that page. Don't turn it yet, Victoria. Yeah, it's really interesting the way the proof works, and kind of using this midpoint here, and a midpoint here, along with they locate the midpoint of this piece, and the midpoint of this piece, and the midpoint of this piece, and they're able to construct, as you can see, a parallelogram, kind of going across from inside here. Turn the page, and you'll see a 22-step proof. And that is why we are not going to do the proof together. It's already done in your book. Read over it as you will, but for our purposes, we're not even gonna mess with that proof. I do want to bring something to your attention, though. I want you to consider for a moment a triangle that has all 3 sides equal. Of course, we would refer to this as an equilateral triangle. And keep in mind, we said that an equilateral triangle is all 3 sides equal, which means it does have at least 2 sides equal, which means it is isosceles. And we said that if you were to draw the angle bisector between the 2 equal sides or the legs of an isosceles triangle, this line will bisect that angle. If you were to bisect the angle, it'll bisect the opposite side, we call it usually the base, and it'll be perpendicular to it. What that means is this is a perpendicular bisector, it is an altitude, it is an angle bisector, and it is a median all at once. Say it again. This is an angle bisector, a perpendicular bisector, it's a median, and it is an altitude all at once. But so would it be if I were to go this way. It's an angle bisector, it's an altitude, it's a median, and it's a perpendicular bisector. So the same would be true here for this one, right? So therefore, this is the circumcenter, because the perpendicular bisectors meet there. It's the incenter, because the angle bisectors meet there. It's the orthocenter, because the altitudes meet there, and it's the centroid, because the medians meet there. So for an equilateral triangle, the circumcenter is the same as the incenter, as the same as the orthocenter, is the same as the centroid. So kind of a neat thing to see there with an equilateral triangle. Turn over to page 114, if you would please now. Page 114. And normally, Victoria, the class would read all of this aloud. I just pick people to kind of read as we go through. I'm going to highlight some things for sake of time. I would encourage you to carefully read over this and maybe put a sticky note in this page. Going to be beneficial to you. All right. Triangles congruent. You already have these. You better have these memorized by now. Angle, side, angle, side, angle, angle, side, 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 angle, side. Okay. Right triangles congruent. Leg, 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 angle, hypotenuse, leg, hypotenuse, angle. Again, you better know those. 2 angles are equal. Well, If they're straight angles, all straight angles are equal, all right angles are equal, vertical angles are equal. Put a star next to number 2. Complements or supplements of the same angle, or complement supplements of equal angles are equal. That's good to know. Of course, number 3, right, CPCTE, right, corresponding parts, corresponding angles of congruent triangles are equal. Put a star next to number 4. Angles opposite equal sides in the same triangle, right? We try to pound that. Isosceles triangle, 2 sides equal, clang, angles equal. Number 5, of course, alternate interior or corresponding or alternate exterior. That's not written here. Angles when lines are cut parallel. Lines are cut by a transversal. Number 6, remember we said if 2 angles have their sides parallel, right side, left side, left side, the angles are equal. Or if 2 angles have their sides perpendicular, right side, left side, the angles are equal. So not one we'll use often, but we will see it again. And then lastly, by use of axioms, that just means you use the addition axiom to say the equals and added to equals, and then you use a substitution axiom, and then we subtract something away, and hey, look, they're equal. Okay, we've done that before. You know, that's all that means there. Lines are equal. Number 1, of course, you could write CPCT. Number 2, the converse of the last one you start. 2 angles equal in a triangle, clang, opposite sides equal. Opposite sides of a parallelogram, also equal. Segments between parallels, which could equal segments from another transversal. Okay, so more recent theorem there. And of course, axiom use as well. Lines parallel. How to get lines parallel? Well, if alternate interior angles, alternate exterior angles, corresponding angles equal, you see that there. If 2 lines are parallel to the same line, or if 2 lines are perpendicular to the same line. If they're opposite sides of a parallelogram, and if the sum of the interior angles on the same side of a common transversal equals a straight angle. We almost never use that because there's always an easier way, but technically you could. Angles are unequal if they lie on the opposite unequal sides in the same triangle. Quick refresher, been a little while since we reviewed over this, but we said if this side is bigger than this side, then the angle across from the big side is the big angle, and the angle across from the littler side is the littler angle. Okay, the smaller angle, the lesser angle, if you want to use the math term. If one's an exterior angle, the other's an opposite interior angle of the same triangle. So remember we said an exterior angle is always bigger than either one of these 2 opposite interior angles, and for that matter, we noted earlier, it's equal to the sum of the 2 of them together. We've also talked about you cut off unequal segments from the foot of a perpendicular. Okay, so that was more recent as well, remember. So there's a perpendicular, you pick a point, and you cut off a little segment, and you cut off a bigger segment. Bigger line cuts off a bigger segment. Smaller line cuts off a smaller segment, you know. We won't use that one particularly often in proofs either. And put a star next to Roman numeral 8. How to prove a quadrilateral is a parallelogram. If opposite sides are parallel, if opposite sides are equal, if 2 sides are equal and parallel, if diagonals bisect each other, if 2 pairs of opposite angles are equal. That's not one we've proven yet, so maybe cross out number 5. We can't really use it because we haven't proven it, though it is true. We could prove it, we just don't need to. We've got enough other things working for us. If 2 pairs of adjacent angles are supplementary, it could work as well. Really the big 4, those first 4. Again, in number 5 and 6, we've proven those are true if there's a parallelogram. We never proved the converse, so don't use those in proof. They are true, though. But 1 through 4 are your big ones, so maybe cross out 5 and 6 for our purposes. If you need an auxiliary line, how will you draw it? Well, 2 points determine a straight line, right? So just joining 2 points. But you might say only 1 line can bisect a given angle. You might say that through a point, only 1 line can be drawn perpendicular, or through a point, only 1 line can be drawn parallel to a given line. You could simply extend the line. We did that in the homework proof last night, right? We extended that median out to some random point where it would intersect another line. Number 6, marking off the shorter of 2 lines on the longer. And that's kind of what we did in a couple of our proofs, especially some indirect proofs we've looked at. And of course, making another line at an angle equal to a given angle as well. Turn the page now. And analytic and synthetic methods of proof. Terms definition section. You might still be there from when we talked about the centroid. So if so, that's good. If not, turn to terms definition section. And couple ways to do proofs. And I've alluded to these without using their names. So we're going to give some names here. The first thing I want you to write down is the synthetic method of proof. the synthetic method of proof. I'm going to use this term quite a bit. Synthetic method of proof begins, here's your definition, begins with what is given. Begins with what is given. And makes known statements, begins with what is given and makes known statements until it reaches the desired conclusion. The synthetic method of proof begins with what is given and makes known statements until it arrives at the conclusion. Our homework proof was a perfect example of a synthetic approach to proof. The synthetic method, you simply clang, this is true. Well then, clang, this is true. Well then, clang, this is true. And lo and behold, next thing you know, I'm done with the proof. Here's the problem. It doesn't always work, right? Sometimes you do make all your clang statements and you're not done yet. That's where we have to look at what we're trying to prove and say, now how do I figure this out? What am I missing? How do I get that? That's what we call the analytic method of proof. The analytic method, or sometimes called the analytic approach, but the analytic method of proof. Now, in its strictest sense, to do a proof using the analytic method, you would begin, here's your definition, begin by focusing on what is to be proven. Begins by focusing on what is to be proven and determines which statements are needed to reach that conclusion. The analytic method of proof begins with what is to be proven and determines which statements are needed to reach that conclusion. The analytic method of proof. Now you can see the difficulty with this. All right, I need to prove these triangles are congruent. How do I do it? Well, I could either do side, 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 angle, or side, angle. Oh. Well, let's pick one at random. Let's just say we want to go with side, side, side. How do I get side, side, side? Well, I need sides. Okay, are there any sides I can get equal? Well, I can maybe get these sides equal this way. Oh, good. How about these sides? Ooh, I don't know. How about these sides? Ooh, I don't know. Well, forget side, side, side. Let's go with side, angle. You can see the challenge that's presented in the analytic method. Because what if there's lots of ways to get to that conclusion, right? So the analytic method in itself is insufficient. Certainly the synthetic method of proof, other than maybe last night's proof and a few others we've done, insufficient. So the best approach to proof. Put a star next to this in your notes. This isn't something from your textbook. This is just for me. The best approach. Begin technically synthetically, but begin with the synthetic approach, if you will, by focusing on clang statements. And it's what we've done on every single proof we've done together. Every time I say, are there any clang statements? Let's see, what clang statements do we have? So you're in the habit already of beginning synthetically by saying, what do I have? What's in the given that's really useful to me? And then when we run out of clang statements, I always turn the conversation. I say, okay, now, do we have what we want to prove yet? Okay, how can I get this? So we've been starting synthetically and ending analytically, and that's the best approach. Start synthetic, get all your clang statements. That gives you ammo to work with. That guides your thinking when you get to the analysis. If you don't do the clang statements, you're going to go to the analysis clueless, because there's lots of ways. We will start synthetic, clang statements. Then when you run out of them and you switch to the analytic method, what do I need? Well, I've already got these things, I'm just missing this. Okay, how do I get that? Oh, I could do this. And now the proof becomes easy. Start synthetic, end analytic. That's the best approach to proof. Let's kind of look at some general suggestions here at the bottom of page 116. Make an accurate drawing. Okay, now so far you've been given those drawings. Okay, those drawings are going to run out. Okay, pretty soon, well, I say pretty soon. Eventually, I will give you words. You will figure out the picture. Make sure it's accurate. Make sure you don't assume something that's not stated. Okay, but make an accurate drawing. State specifically in terms of lines and angles. Don't just say, I've got lines equal. Which lines are they? Well, it's AB and GS. Whatever, okay? Figure out which lines are actually given equal, which lines you're trying to prove equal. Number 3, I love this. Recall the various ways of proving this required relation of parts. In other words, figure it out. Okay? What are the different ways of doing this? That's the analytic approach. What are the different ways I can prove this? Determine the most probable method. What method probably is easiest? Well, if you've done plain statements, you can determine which is easiest. Note what's known and what's lacking. Again, if you do the Clang, you already know what's known. And when you go to the analytic, you're going to quickly figure out what's lacking. Study how to get the parts that are lacking, either by a reapplication of steps above or maybe a construction line. Number 7 says, when direct method's not apparent, try the indirect method. You may have noticed we've done that occasionally. We'll do that more throughout the year where, well, I don't know what to do either. All right, let's ditch the direct method. Let's try the indirect approach. You're not going to do that on quizzes or tests, okay? We'll do it in class sometimes, but on quizzes or tests, the direct method should be readily available to you. And when two magnitudes are given unequal, marking off the lesser on the greater often suggests a line of proof. And we've done that before. Theorem 3, Theorem 6, Theorem 6 I think is where we did it. Not Theorem 3, but Theorem 6, marking off the lesser on the greater, an opportunity. And we'll work more with inequalities as time goes on. We've worked with some already. All right, let's take a look at a proof together then as we kind of round out the hour here. Page 118. And let's do proof number 3 together. All right, so we'll round out the hour with number 3 there on page 118. The picture is already given to you. We'll copy that down on another sheet of paper. We've got some triangles that are overlapping each other. We've got a triangle AED. But it overlaps with another triangle such that we've got this point F, and it goes up to C, which comes down to B. But B is such that A to F and B to E are equal to each other. Okay, and then a line goes up here, and then this line AD that comes up is the same length as this line BC. And we don't know the name of this point. There's a reason for that. It doesn't matter. Okay, you don't need the name of that point. We're not going to use that point in the proofs. They're trying to help you out here. So what are we given? Well, you'll notice it doesn't say given, colon, but it says if these things are true. That's your given. If AF and BE are equal. If AD and BC are equal. And one more. If DE, this whole line, equals CF, this whole line, then prove that triangle AED is congruent to triangle BFC. All right, once you got that down, 2 columns, statements, reasons. Go and get down your first statement and your first reason. We got AF equal to BE. We've got AD equal to BC. And we have CF equal to DE. All right, pause the video, Victoria, if you need a little bit more time to get that copied down. All right, really no Clang, right? There's no words like midpoint, perpendicular, bisector, anything like that. We're not given 2 sides of the same triangle equal either. Now we do have 2 sides equal, but they don't form a triangle, so we can't say Clang equal angles. But as we're looking to prove triangles congruent, if I just look at the given, there's one thought that resounds in my mind. I've got these sides equal, and those sides equal. I should be thinking, yeah, hopefully you said side, side, side. Here's the problem. They're not actually 3 sides. Now, DE and CF are sides of these 2 triangles. So there's a set of sides right there. And for that matter, AD and BC are indeed sides of the triangles. So there's another set of sides there. But AF isn't a side of the triangle. It's only a part of the side of the triangle. Similarly, BE is not a side of its triangle. It is only a part of the side of the triangle. Victoria, what are the two other sides? We've got CFDE, we've got AD, BC, but which sides do we not have equal? Yeah, hopefully you said AE and BF, right? They're not listed as being equal. You realize, though, if I could get them equal, I've got side, 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 I'm done with the proof, right? This is the purely analytic proof. We did a purely synthetic proof for homework last night. We're doing a purely analytic proof right now. If I want to get these triangles congruent, I've already figured out side, side, side is my best way, because I have a whole bunch of line segments. I don't have any angles equal. If I could just somehow get, I'm going to come down a little ways, AE equal to BF. If I can get that statement, then I'll be able to say that triangle AED is congruent to triangle BFC, and it will be my side, side, side. Now, I don't know what numbers those statements are going to be yet. I don't even know if I left myself enough room. But I know the proof is going to end with that statement. I've concluded I'm going to use side, 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 and I'm going to be able to use it because I'm going to have AE, the whole thing, equal to BF, the whole thing. Even though right now I only have AF, the part, equal to BE, the part. But I know I'm going to be able to get the wholes equal. I've been emphasizing some words, Victoria. I'm sure you're screaming at your computer right now. What should we be thinking when we've got wholes and parts? Yeah, absolutely, the whole equals the sum of its parts. Yeah, let's go ahead and start by saying, well, AE is equal to AF plus FE. And I know that BF is equal, I'm trying to read my writing here, BF is equal to BE plus FE. I know that's true because the whole equals the sum of all its parts. So, if I want AE, the whole, equal to BF, the whole, then the sums of the parts would need to be equal, correct? Somehow, some way, you understand that if I could say that AF and FE together equal BE and FE together, then I could substitute an AE right here and a BF right here, right? So I'm going to get this statement by simply substituting the wholes in for the sums of the parts. The question is, how do I get this statement? Do you see how we're working kind of backwardsy? Analytically. How do I get this? I know what I need. Okay, how do I get it? Well, I was given that AF and BE were equal, right? What do I know about FE and FE? Well, it's the same line. It's equal to itself by... Yeah, so if I said that FE equals FE by identity, then I've got equal quantities being added to equal quantities. Well, we've we've accepted, earlier in the year, that if equal quantities are added to equal quantities, the sums are equal. So this has to be true by number 4, the addition axiom. And therefore, this is true number 5 by the substitution axiom, which means the triangles are congruent number 6 by side, side, side. I kind of worked my way backwards. What do I need to get that? Had some clangy thoughts from thinking whole and parts so much. And there we go. Came together, really done purely analytically in this case. All right, for homework, you're going to get a chance to try one yourself, and that is page 119, number 5. Page 119, number 5. The picture's provided, the given, the proof is provided. Go and copy that on your paper, do the proof, and we'll take a look at that in our next lesson. Have a wonderful rest of your day.